Hello. In this video, I'm going to go over the basics of solving a statically indeterminate torsion problem. As you can see, this problem setup is somewhat simple. It's just a completely uniform geometry segment, cylindrical shaft. This is viewed from the side, 100 inches long, diameter of 2 inches, and at exactly halfway across, there is a counterclockwise torque applied that is 80 foot kips or 960,000 inch-pounds. And what makes this indeterminate, as you can see over here, I have a summation of moments. You have an unknown torque in the left clamp, an unknown torque in the right clamp, and that load in the middle. This is two unknowns, one equation. You cannot solve that. It's an indeterminate problem, being that we don't know what's happening at either side of these clamps. Also, do notice that these clamps, some problems you will see that there's an amount of misalignment or slip where the shaft is allowed to twist a certain amount before the clamp engages. However, in this problem, it's just simple. Clamps are engaged at all times. There's no allowed slip. So let's go ahead and input this information into our program. So first things first, breaking it down into segments. Remember that segments consider geometry but not the load, any forces applied. So our entire shaft, it's just completely uniform geometry. So we only have one segment. The length is 100 inches total, an outer diameter of 2 inches, and a shear modulus of 12,000 KSI. Do note that the base unit of length that I'm using in this is inches instead of foot. Inches is common to see because in some units you'll be using PSI and so on, which use inch as the basic unit. So instead of having foot kip, foot pounds, breaking it down into inch pounds. Moment of inertia, I've calculated here. Number of torques, just one. It's at 50 inches from the left, and it's counterclockwise, so it's positive. 960,000 inch-pounds. And it's clamped on both the left and right end. There is no misalignment, so you can either enter 0 or just leave it blank. One segment, two sections because of that load in the very center that's breaking it into two sections. Okay, so now it has it drawn, and you can see the three main steps of this process, exactly the same process when approaching axial loading indeterminate problems. First step, remove the right clamp. Now you have a determinate problem. Solve for the net twist. Step 2, still remove that right clamp, but also remove any loads on there and apply a unit torque on the right end, and then solve for net elongation, or in this case twist because it's torsion. Once you have both of those net twists, say net twist 1 from step 1 and then net twist 2, once you have those, you can calculate what the reactionary load in the right clamp is. Once you know that, then you can solve out the problem as a determinate problem. This pop-up goes over that. Okay, so step 1, starting from the right, working towards the left, we have over here, we have section 2. You can see there is no reactionary clamp on the right side, so that just leaves no loads applied in section 2. Therefore, you can just put in 0. There's no amount of twist when there's no loads applied. Then, analyzing section 1, you can see that I have calculated here stress and strain, but we can ignore those. I also have them calculated in step 2, but you can ignore those. We're just looking straight to go for what is the twist, which in this case, from that 80-foot kip, comes out to 2.546 radians. Okay, so that's step 1. Now I can move on to step 2. Do note that it asks for you to just put in the net twist of the entire segment, unlike problem 1. And due to this problem being completely symmetrical with the load applied at the very center, that means that section 1 and 2 are of equal length. So the net twist in either section is going to be the same. So on the right here we have the analysis for section 2. We can really ignore these stresses and strains, but do note that they are the same in both sections. And then we come down to our twist, and you're more or less doubling it. And that twist is very small, but remember it's just a unit load. Okay, so now that we have section 1 and 2 done, and it lists these here what the net twist is, the program automatically calculates what the torque at the right clamp is. And I'll show you how that's calculated. So in my PowerPoint I call it step 3, but the program ignores that step. So anyway, it's with this equation here. It's the negative of net twist 1 over net twist 2. And that comes out in inch-pounds of what the right clamp is. Even though, strictly speaking, that equation would be a unitless answer, we know that it's coming out, this is giving us that torque. And it follows standard sign convention, so this one comes out to be negative, which means that the reaction in the right clamp is going to be in the clockwise direction, which also fits what it should intuitively being both of these clamps to resist that counterclockwise torque in the center. Both of them should be in the clockwise motion. So we can move on to our final step, where we solve through the entire problem with that torque from the right clamp applied. So starting with section 2, see I have my summation of moments, stress, strain, and net twist. And now it's actually asking for those stress and strains. So the outer torque, let's see, inch-pounds. Outer shear, it's really just the shear, let's see. Okay, and the twist, the program doesn't ask for strain, but I have it calculated anyway. Do note that for the shear, it's asking for the magnitude of the shear. So even though this is coming out as a negative, we're just looking for the magnitude. Those are all accepted, and we can move on to analyzing step 1. Okay, so here's step 1. Now we have our summation of moments, and do notice that it's actually, all of these values are coming out to the same as in step 2. It's due to this problem being completely symmetrical. That means the force in the left clamp that you can find from the summation of moments, the torque in the left clamp, it's the exact same as the torque in the right clamp, just completely symmetrical. However, the signs are reversed in this one. So let's put those in. Solution complete. And you can see the net twist overall, and this is regarding it at the right end is going to be 0, which it has to be 0 because the right end is clamped. It cannot move. So we know that it's working out. If that net twist at the end of this was coming out to any value, if it was a very small, very, very small value, then you just have some error in your rounding, which is acceptable. But if you have an appreciable amount of net twist in the end, and that can't be right because it has to be having a 0 net twist. So that's basically that. That's how you approach just a very basic, that's the 3 or 4 step approach for an indeterminate torsion problem. It's really very similar, almost exactly the same as an axial loading problem.